Okay, let's talk about frequency distributions. So the first thing we want to talk about are frequency tables and how to generate them. And then we'll talk about tests of independence and some more graphs that we can use. So let's first talk about generating tables. So the main functions for generating tables are table and xtabs. So variables for creating tables must be factors or coercible to factors, so they could be character variables. So here's how you use the table function. You just input the factors one at a time, or xtabs once this notation. So you use this tilde, factor 1 plus factor 2. And the main reason for xtabs is it can do a little bit fancier stuff that will be beyond the scope of this course. So first of all, we want to install this package, BCD. When you run this code, it will ask you to select a crayon mirror and so on, so follow the instructions. Once you've installed it, then load it. And in this package is an arthritis data set. This package, some of the functions we use today will also be in this package. So you can read a little more about this arthritis data set. It's a data frame with 84 observations and 5 variables. So it's a clinical trial, results from a clinical trial where we had a treatment, placebo, versus a treatment group. And we had gender, female, male. We had age of a patient, and then improved, whether or not no improvement, some improvement, or marked improvement existed. And this is investigating rheumatoid arthritis. Okay. So first let's run attach. I've already ran it a few times here. So detach. And just to check, it's always a good idea to run structure of arthritis, and you'll see that we have ID in this variable. We have treatment, sex, age, improved, and improved is an ordered factor with 3 levels, and age is a continuous interval variable, and sex and treatment are factors with 2 levels. So let's start with basic one-way tables. So I've attached the data set. So improved is just this guy. So I can just look at one variable. So I can create a table easy enough of my count. So there were 42 people that showed no improvement, 14 showed some, 28 showed marked improvement. If I wanted to use xtabs in the VCD package, I would use this notation, tilde improved, data equals arthritis. I probably want a two-way table to learn a little bit more. So here's how I make a two-way table of improved by treatment. So here I have, for example, in those people that showed no improvement and were in the placebo group, there were 29 of those. There were 7 people that showed marked improvement in the placebo group. 21 people showed marked improvement in the treated group, and so on. The xtabs uses this notation. Again, you don't actually have to list data equals arthritis because I've already run attach. So improved exists in my workspace. So it's important to know which you have in your rows and which you have in your columns. Oftentimes we would want to put the explanatory variable on the rows, or at least I like to, and then the response variable, so the response is whether or not they improved or the amount of improvement. I like to put that across columns. So how did I switch rows and columns? I just changed the order. So I put treatment first and then improved second. So you can think of this as X and Y. So you could also notice that if I had improved in treatment, I could just take the transpose of that, which flips rows and columns. So here is some graphical displays of two-way tables in the VCD package. Here's a nice one that's quite useful. We don't know what some of this stuff is, but you can see here, if you looked at the table, What do we have? We have a lot of people in the placebo group showing no improvement, so it has a bigger box here. As compared to the treatment group, there were a lot fewer people showing no improvement, and so on. About the same proportion of people showed some improvement, and over here in the placebo group, this red box, the proportion or the amount of people showing marked improvement is small, at least compared to this blue box, where a lot of people in the treatment group showed marked improvement. We'll learn about these residuals later. So let's look at three-way tables. Three-way tables are a little bit harder to display, so we'll need some tricks, but here's the idea. If I just run the same notation, factor 1, factor 2, factor 3, so I have treatment, improved, and sex. It'll start by saying, here's the female table, and it'll construct a treatment by improved table, so a 2x3 table for females, a 2x3 table for males. So here we have all three variables displayed. So for example, I could say there were 19 females in the placebo group that showed no improvement. There were, for example, no males in the placebo group that showed some improvement, or 5 males in the treated group that showed marked improvement. So one question we might want to ask ourselves in this study is, do any relationships, does the drug work the same across gender or not? So that's where we're going towards. So margins, we often create a k-way table but look at one factor at a time. So for example, above we created a three-way table. So we had 3 factors with each with either 2 or 3 levels. So we often start with our finest level. So we look at the complete, or our finest table. So we look at a k-way table, and then we marginalize over some of the factors as needed. Okay, so here's the pseudocode. Margin table, my table, and then you just input the margin numbers. So these are 1, 2, or 3, or other arguments it'll accept, I believe. So these are the margins that you're keeping. You can also add margins, which will add row sums, column sums, etc. So for example, let's create this table. This is the one we really just looked at. I just want to save it now as a table. So I have treatment first, then improved, then sex. Okay, so treatment is the first margin, improved is the second margin, and sex is the third margin. So if I wanted to look at treatment, if I wanted to marginalize and just look at the results for the treatment, I would enter 1 because it is the first variable. So this will tell me I had 43 people in the placebo group and 41 in the treatment group. If I look at this guy, what's the second factor listed? Up here. When I created this guy, improved. So I wanted to see what's the improvement. So I had I had 42 people showing no improvement, 14 showing some, and 28 showing marked. And I could also look at gender. So you do see I have a lot more females in this study than males. I probably want to look at a couple of margins at once. So specifically, I want to at least look at this guy. So in the placebo group, so I've marginalized by keeping the treatment and the improvement variables. So the first 2 variables are of interest, and I've summed up over the sex variable. So here you'll see I have 29 people in the placebo group showing no improvement, and so some of those people were females and some of those people were males. I had 21 people in the treatment group showing marked improvements. Some of those were females and some of those were males. So excuse me, all this function really did was add females and males. So for example, here's my females, here's my males, and if I add these together, 19 plus 10 is 29. and the other total sum of 2. Okay, so that's all that did. I can add margins. What's this going to do? It's going to add the sum. And the sum here, I have 1 and 2, so it added row sums and column sums. What's this going to do? It's going to add just column sums. Okay, so just different ways to summarize tables. I often want to summarize, or actually I want to often report proportions more than counts if I'm interested in determining if improvement depended on treatment group, for example. Proportions are most meaningful. So typically we look at row or column proportions. We might also want to print out a flat table, and I'll show you what that is in a moment. So it's just a little bit nicer than our three-way table. And I want to remark that we want to do our proportions before adding margin sums. Otherwise, it'll think the margin sums are actually a variable, and they're not. They're just a summary. So let's look at some pseudocode. So I want to do proportion table, and then I input my table and margin numbers. So do I want to do row proportions or column proportions or both? And you usually do F table, my table. And again, read the help files for these to understand more. There are a lot of options that we won't cover here. So first of all, remember what this line of code does. This marginalizes, so we're going to ignore sex, so it's just going to look at treatment and improvement. And so I'm going to save this as treatment improved table, just to make it a little easier to work with. And what did this do? This looked at row proportions. So to verify this, you'll notice that I had 29 plus 7 plus 7. So 0.67 is 29 divided by 29 plus 7 plus 7. Okay. So just to make sure we're all on the same page with how we would interpret what these numbers mean. So here I would say, for example, in a placebo group, what percent showed marked improvement? So given that I'm in a placebo group, that means given that I'm in this first row, there were 29 out of 29 plus 7 plus 7, or 67.4% showed marked improvement, while what percent of patients in the treatment, marked improvement, excuse me, 16.27 or 16.3% showed improvement, so 7 out of 29 plus 7 plus 7 showed marked improvement, while what percentage of patients in the treatment group showed marked improvement? 51. So here, these are the most meaningful percentages to report. For example, I would want to make a statement of the effect that 51% of people in the treatment group showed marked improvement as compared to 16% of people in the placebo group showed marked improvement. So that's a little bit more meaningful than just reporting these numbers. So 7 versus 21 doesn't mean a lot, because it could be the case that I just had a lot more people in the treatment group. So if I had 3 times as many people in the treatment group, I should anticipate, even if nothing's happening, 3 times more people to show marked improvement in the treatment group. So the proportions take care of that for us. Okay. Question: would we interpret column percentages? So let's show you why not. So what would this mean? So here I would be making a statement of the effect of those people that showed no improvement. 69% were in the placebo group. So this is a much less meaningful thing to say because placebo and treatment were not random. These are explanatory variables. The response variable, or the response, is none. So we usually want to fix the explanatory variables and report the proportion of responses in each explanatory group. So that is whether or not they showed whether or not they were in the placebo or treatment group is less meaningful as an outcome to report, because the outcome is that they showed no improvement or some improvement or marked improvement. So we want to focus on saying in this group no improvement, in that group then they showed no improvement. So the response is the outcome. Placebo and treatment is the explanatory variable. So we would always do the row percentages in this case. All right, and let's look at F table. So here, F table stands for flat table. So here, this is just a little bit difficult notation to look at. So F table, all it does is organize this a little bit for us. So for example, here I have this placebo group, and in the placebo group I can look at none, some, or marked, and then I can look at female or male. So for example, in the placebo group I had 19 females that showed no improvement. So placebo, none, female, 19 people were in that group. Treated, some, male, 2 people were in that group. Now let's talk about tests of independence. Let me also say we can add margins also. So it becomes a little bit difficult to look at, but we could look at placebo, none. There were a total of 29. Placebo, some. Placebo, some improvement. There were a total of 7. Of those, 7 were female and 0 were males. And then I could look at, what about this number 32? This is if I sum these guys, 19, 7, and 6. So this is females in the placebo group. Okay, 11 males in the placebo group. Okay, let's look at tests of independence. So our main test is the chi-squared test of independence. So recall that a chi-squared test of independence for a two-way table or a J by K table tests that row proportions are the same across columns, or that column proportions are the same across rows. So recall just a little bit of review for a chi-squared test statistic. Under the null hypothesis that X and Y are independent, we can compute expected counts as the total counts times the row proportion times the column proportion, and then we can get an observed count. And what's the chi-squared statistic do? It says, let's look at how far the observed counts are from the expected counts, square them, divide by E, and then sum up all of those guys. So in a 2 by 2 table, there will be 4 O's, 4 E's, and you'll take this statistic. So where does this come from? It's important to note, what is this guy? O, the observed count minus the expected count over the square root of the expected count. That is called a Pearson's standardized residual. So the idea is that O has mean E and standard deviation, square root of E under a Poisson distribution. And if we use a normal approximation, then this guy has mean 0, standard deviation 1, and can be roughly approximated with a normal 0-1 distribution. And so the chi-squared statistic is squaring up in a 2 by 2 table case for the square of 4 standard normal distributions under the null hypothesis. The distribution that we compare it to has, we compare the test statistic to a chi-squared distribution with degrees of freedom, number of rows minus 1 times number of columns minus 1. And sometimes we'll use Fisher's exact test instead of a chi-squared distribution. And when we use that is when the O minus E over E squared, or this guy, O minus E over square root of E, does have mean 0 and standard deviation 1, but it might not be reasonable to use a normal approximation for that guy. When a normal approximation works well is when E is large, say larger than 5. If it doesn't work well, we can use another tool called Fisher's exact test that doesn't rely on the assumption that O minus E over root E is roughly normally distributed. So here's the pseudocode. I would just run chi-squared test, my table, fisher.test, my table. And so let's look at determining if these proportions are the same across columns. So that's really the null hypothesis that we want to test. So in the placebo group, we had 67% showed no improvement, 31% in the treatment group showed improvement. So these proportions should be roughly the same across columns. So that's what we want to test. You'll notice here that in the placebo group, 67% showed no improvement, 16% showed marked improvement, while here 31% of people in the treatment group showed no improvement and 51% showed marked improvement. So you can see what's really happening is that these proportions are increasing in the treatment group and decreasing in the placebo group. So just to give you a more intuition of what the test statistic is, so here are our Pearson standardized residuals. So this is the observed count minus the expected count divided by the square root of the expected count. So if you run resid chi-squared.test, it gets you those residuals automatically. So where did those residuals come from? So let's look at computing the expected count for this guy. What do? I take the total, which is 84, times the row proportion for this guy, which is 43 out of 84. And then this guy times 42 out of 84. So 43 out of 84, 42 out of 84. The expected count here is, so if we have independence, I should expect 21.5 people to be in this group. How many did I actually have? I had too many under the null hypothesis, so I had 29. So you'll notice if I look at the observed count minus the expected count divided by the square root of the expected count, what do I get? 1.617. That's what that residual is. So a positive residual tells you that too many people were in that group, or more people than should be under the null hypothesis of independence. All right, so here we can run chi-squared.test to get the chi-squared test statistic. But all that really is doing is squaring all of these residuals and summing them up. Observe, indeed, that's the case. If I sum up all of these squared residuals, I get 13.055. The degrees of freedom is the number of rows minus 1 times the number of columns minus 1, so that's 2 times 1. And that gives us our chi-squared test. And it gives us our p-value, which is the right tail area. So the area to the right of 13.055 for a chi-squared distribution with 2 degrees of freedom. So this mosaic, you can read more about the help file here, but what this is going to do, so here notice I have my p-value 0.001. Here's my p-value 0.001. And here it has color coding for my Pearson residuals. So the size of the box represents a residual, and so does the color. So what do I have? I have a positive residual here for the placebo group showing no improvement. So this means there were too many people in this group if in fact treatment and improvement are independent. What happened here? There were too few people in the marked group if in fact the null hypothesis that treatment and improvement are independent is true. There were about the right amount of people in the sum group for each guy. And then you'll notice here I have blue residual here for this group, which says that there were too many people that showed marked improvement in the treatment group to retain the null hypothesis of independence. You could also make a traditional bar plot, which looks like this. So here I would probably put placebo and treatment group on my x-axis, and I'd like to put the response in my legend. So what does this say? It says the same thing. It says that I had in the placebo group a lot of people showing no improvement relative to the people that showed marked improvement, while over here in the treatment group I have a lot of people showing marked improvement relative to the people showing no improvement. Okay, so the shapes here should be the same under the null hypothesis. All right, one last. Let me just show you one last thing. I can also get Fisher's exact test, and it's just going to give me a p-value of 0.001, which is about the same. And the reason these are going to be about the same is they should be the same when we have large expected counts, because that normal approximation is working well, so we can rely on it. Just to show you when they might be different, let's suppose I have this fake data set, so I'm just making up this table because the counts here are small. So what happens when I run chi-squared test? It depends on large sample stuff. It says chi-squared approximation may be incorrect. So those Pearson residuals, it's not reasonable to use a normal distribution to model those guys. And hence the test statistic, which relies on that assumption being true, is maybe not reliable. In this type of setting, you can always use Fisher's exact test, and it always works. So it does not rely on any normal approximation. You can take a MathStat course to rely more on what that is. It's actually a hypergeometric distribution you can derive. Okay,